Hello everyone, welcome to the lecture series on feedback amplifiers. For the last video we had studied about loop gain and solved some numericals. In this particular video specifically you're gonna see some of the advantages or characteristics of negative feedback amplifiers. The first one is gain stability, then nonlinear distortion, noise, increases bandwidth, increased input impedance and reduced output impedance. The first three, that is provides gain stability, reduces nonlinear distortion and reduces noise. These characteristics of negative feedback amplifier we are going to study in this particular lecture video. The first one, stabilization of gain with negative feedback or desensitivity of gain. Now usually whenever I consider an amplifier, it has its gain, okay. Now when I say amplifier, it is without a feedback, what I am talking about, okay. And gain of an amplifier is not constant usually, and we had seen in EDC1 also that a lot of factors are there which affects the gain of the amplifier, like temperature or shift in the operating point. These all things we had seen, okay. So in this particular case, what will happen is that how negative feedback is helping me to avoid such things, that we are going to see in this particular part, okay. So even if there is shift in the operating point or change in the temperature, still with feedback things can be improved. That's what we are going to see. Let us consider this equation which we had derived. AF is equal to A upon 1 plus beta A for negative feedback amplifiers. Now as I told you all, the gain varies, right? So since gain varies, there is change in the gain, this gain we are talking about, okay, that is open loop gain, or I can say that it is a gain without feedback. So what we need to do is that is the changing factor, so we will have to differentiate this particular equation with respect to A, okay. So if I see there is on the numerator as well as on the denominator there is A, so what I'm going to do is that I'm going to use U by V rule, okay. What is U by V rule in derivatives? It's V derivative of U minus U derivative of V upon V square. So we are going to use that. You can see over here, this is V, that is 1 plus beta A, into derivative of U, derivative of A with respect to A is 1, minus U, that is A, into derivative of V, derivative of 1 plus beta A with respect to A will be, here it will be 0, here it will be just beta. So that is the reason you find beta over here, upon V square. So you have V square also, okay. Now just have a look over here, here there is beta A plus beta A, here there is minus beta A, okay. So this will get cancelled off. So on the numerator there will be only 1. This is what I just now spoke. And what I will do is that I will take this dA over here, okay, and now divide both the sides with AF, okay. We will divide both the sides with AF, that is gain with feedback, okay. Over here as well as over here you can see both the sides we have divided by AF. But what is AF? AF is A upon 1 plus beta A, this we have studied, okay. So we are going to substitute over here only, AF is equal to A upon 1 plus beta A, okay. So this is going to be the state. Now just check over here, this term and this one of the terms will get cancelled off, 1 plus beta A, and here 1 plus beta A the whole square is there. So one of the term will get cancelled off, so you will be left out with this. I will call this equation number 1. Now this is a very important equation. What is this term? It is dAF by AF, which tells me that change in the gain with feedback. This is dA by A, which tells me change in the gain without feedback, okay. And there is one factor which is affecting this particular term, okay. From this equation I can conclude that your change in gain with feedback will be less as compared to that of change in gain without feedback, okay. Why? because this 1 plus beta A term is at the denominator side. Okay, it's at the denominator side, that is the reason I can say, and obviously 1 plus beta A will be quite huge. So any term at the denominator which is quite huge leads to lower this particular term, so there will be less change in gain with feedback. Fine. So these are the things which I had just explained it to you all. Okay, and we can conclude from equation that the change in the gain with feedback is less, change in the gain with feedback is less as compared to that of change in the gain without feedback by a factor of 1 plus beta A. Okay. Again, the same thing I have written over here. What I have done in the next slide is that dAF by AF, this is multiplied, right, on this side. So on the other side, if I take, it will be divided. So over here you can see it is dAF by AF upon dA by A, which is nothing but 1 upon 1 plus beta A. Okay. Now this above ratio is known as sensitivity of transfer gain. Now what is sensitivity? It is the smallest thing which can make your amplifier to react. Okay. Like for example, if at all I give a smallest input to the amplifier, it will be able to give me some output. That is sensitivity. Okay. But I don't want it to be sensitive. I want it to be desensitive. Okay. Because I don't want, the changes to happen due to temperature or shift in the Q point. So that is the reason I want desensitivity factor to be incorporated in the amplifiers. So reciprocal of sensitivity is nothing but desensitivity, which is given as D is equal to 1 plus beta A. Over here it is 1 upon 1 plus beta A. So reciprocal of that is 1 plus beta A. Okay. So this clearly tells me that, if the D factor is more, then your amplifier will be more stable. Okay. The stability of the amplifier increases with increase in desensitivity. Okay. Let us move ahead. Now this is AF, this equation we are aware about. Now let me use one condition wherein beta A is very greater than 1. If beta A is very greater than 1, I can ignore this one. Okay. If at all I ignore this one, the terms will be just A upon beta A. A will get cancelled and you will be left out with 1 upon beta. Let me call this as equation number 2. Okay, what do you observe over here? AF is directly equal to 1 upon beta, which means gain with feedback is only dependent on feedback factor over here. Okay, and not onto your gain without feedback. Okay. So from this I can write for other remaining amplifiers voltage series feedback, current series feedback, voltage shunt feedback, current shunt feedback. These all things we have studied in the last videos. Okay. Now AVF is equal to 1 upon beta. This was more of general equation which we had found out over here. This was general equation which we had found out. Now we are writing it specifically to the amplifiers which we have studied. Okay. Voltage gain, it means it is a voltage amplifier, transconductance amplifier, transresistance amplifier and current amplifier. So here it is AV, transconductance, so GM, transresistance, so RM, and current gain for AI. Okay. Okay, I hope this is clear to you all. So I hope gain stability is clear to you all. How do we achieve gain stability? Now we'll move to the next characteristic of negative feedback amplifier, that is reduction in frequency distortion. Okay, we are going to use the same analogy which we had studied in the previous slide. Okay, for negative feedback, this is the equation which we are aware about, this equation. Okay, now again same thing, if beta A I take it to be very greater than 1, definitely I can ignore this 1 and it will be just A upon beta A, which will be equal to 1 upon beta. Correct? So from this we come to know that gain is not dependent on A, it depends on beta. If at all you all remember, while explaining the feedback concept, I had explained you all the block diagram. Okay, and in block diagram I had mentioned about feedback network. It's a two-port network which can be built using R, L and C, specifically using R. This is what I had mentioned it to you all. You can go and check the previous videos also. Okay. Now, if at all your feedback network itself is purely resistive, okay, which means L and C are not there. L and C are what? They are frequency dependent components. Okay. So, if at all those frequency dependent components are only not there, then there won't be a question of frequency distortion which will arrive. Okay. Because only resistive components you are made use of, and the overall gain will be frequency independent. Okay. So, definitely your frequency distortion will be reduced in a reduced form when you use feedback. Okay, because it is clearly mentioned over here, we have arrived at 1 upon beta. Okay, and 1 upon beta, in the sense beta is the feedback factor. So, it clearly depends only on beta, right? So, with feedback your frequency distortion is reduced. Okay. Second part of the same thing, reduction in non-linear distortion with feedback. Okay. Now, distortion, to consider distortion we need to consider certain things. Let A be open loop gain, this we have seen before also, and AF be closed loop gain. Okay. Let me consider amplifier is producing distortion D without any feedback, meaning this is for open loop. For closed loop, let us consider DF to be the distortion. Okay. Let me consider this particular figure which we had studied earlier also. Observe the block diagram very carefully. Okay. Let me consider DF to be the difference signal, input signal over here, but I have added certain things over here with zero distortion. Okay. The thing is that when I say a negative feedback is introduced in an amplifier, if at all any distortion is introduced by this amplifier, then it will be reduced, okay, in this particular manner. But if at all distortion is coming from outside, like for example an input signal only is distorted, then there won't be any hopes that the distortion will be removed. That is the reason I have said over here input signal with zero distortion. Okay. Another thing to be observed over here, just see over here, distortion D introduced by amplifier A, which means amplifier has introduced some distortion. Okay. DF is the difference signal that I have considered, and output signal is D. Okay. Now, if at all DF is the difference signal, it will be multiplied with A, and what you will get, D is equal to A DF. This ADF is given to the feedback network, which will be multiplied with beta. So, what you are going to get, beta ADF. Okay. Now, this is minus, this is plus. So, this is capital D. The difference signal will be DF is equal to capital D minus beta A DF. Okay. I hope this is clear to you all. This is what I was talking about. DF is equal to capital D minus beta A DF. Okay. Now, from this what I can do is that I can rearrange the terms. Okay, DF terms I can get together. So, D is equal to DF plus A beta DF. Now, from this I can remove DF common. So, I will remove DF common, it will be 1 plus beta A. So, from this I can write DF as D upon 1 plus beta A. Okay. Now, what is DF? It is nothing but distortion with feedback. D is distortion without feedback. Now, DF is inversely proportional to this particular term. Again the same thing, your denominator will be very large. So, what will happen to DF? It will be very less, which means with feedback distortion is reduced by a factor of 1 plus beta A. Okay. I hope this is clear to you all. Okay, this note I have already discussed with respect to input signal. If at all input signal itself is having distortion, then there won't be any distortion cancellation that will take place. Coming to the third one, that is reduction in noise with feedback. Okay, this is similar to what I spoke about distortion. Again, only thing symbols will change here and there. Okay, so noise is reduced in the same way as that of distortion. So again same factor, okay, and I write, instead of df I have written nf, instead of d I have written n. That's the only change, okay, but the rest theory of this remains the same as that of distortion, second part, okay. Again note remains the same, instead of distortion only noise will come, okay. If at all input signal is noisy, then there won't be any noise cancellation that will take place, but if noise is introduced by amplifier, then it can be corrected by using feedback. Let's look out for some numericals. Let's read it. An amplifier with closed loop gain of 100 is required, and this gain should not vary more than 1%. First of all, amplifier with closed loop gain of 100. Okay, closed loop in the sense it is with feedback. Okay, is 100. AF is given as 100, and it should not vary more than 1%. Okay, when the inherent gain of an amplifier without feedback varies by 20%. Without feedback, the change in the gain is 20%. With feedback, the change in the gain I want is 1%. Okay, find AV and beta. This is quite simple. Okay, variation in the open loop gain, I told you all, without feedback the gain variation is 20%. What do you mean by variation? We had just seen some derivation, okay. So in that we had seen that dAV by AV, okay, which means it is open loop gain variation, change in open loop gain, okay, which is given as 20%, so it is 0.2. Similarly 1% is given dAVF upon AVF is equal to 1%. So from these two things, okay, I know that the ratio of dAVF upon AVF whole divided by dAV upon AV is nothing but 1 upon 1 plus beta I. Okay, this we had just derived, so I am going to make use of that. Substitute what all things you have. You have this ratio, you have this ratio, you don't have beta, you don't have AV, okay, because both are asked to find out. Okay, so what you will get is beta I. Okay, so get that, substitute and get. Okay, so I have got it as 19, but you all check the values later. So beta is 19. Now open loop gain, okay, you know that AF or AVF is equal to A upon 1 plus beta I. So from that AV is what? AVF multiplied by 1 plus beta I. Okay, beta AV I have already found out, okay, and AVF is given to us in the problem, okay, here 100, and this beta I we have found as 90. So substitute, see if you are getting 2000. Okay, this is AV. So first part of the problem is over. Now we need to find beta. Beta AV is 19 and AV we have just got, so just substitute and see if you are getting this. Okay, I hope the first problem is clear to you all. Moving to the next problem, they have given us the open loop gain AV is equal to 10,000 and feedback ratio of beta is equal to 1 upon 10. Then for negative feedback, find a percentage change in the closed loop gain. Closed loop gain in the sense with feedback. What is asked is dAF upon AF, that is asked. Okay, when open loop gain varies 50% with temperature. So variation in open loop gain is given, that is dA by A is given to you as 50%. Okay, just jot it down what all things are given. Now first of all we need to find AVF. Okay, so AVF will be AV upon 1 plus AV beta. Okay, substitute, all the things are present with us, so you'll get some answer, please do check. Now open loop gain variation is given to dAV by AV is given to us as 50%. We'll use that formula, okay, which we had derived. dAVF upon AVF is equal to dAV upon AV into 1 upon 1 plus beta AV. Substitute, because we have all these parameters, we'll get some answer. They have asked percentage, So we have to convert it into percentage. Okay, please do check these answers. Moving to the next problem. An amplifier has an input of 10 millivolts and a gain of 200 without feedback. Without feedback, so A is given to me, or AV I can say is given to me as 200. Okay. The distortion produced at the output is 10%. D is given to me. Okay. Distortion produced at the output of the amplifier is 10%. Okay. It is desired to reduce the distortion to 1% by using negative feedback. So with negative feedback it should be 1%, that is DF should be 1%. Here it is D should be 10%. Calculate the gain and the output voltage with feedback. Let us start. So as I told you, distortion without feedback and distortion with feedback are given to me. Okay, so it's been put up accordingly. Amplifier without feedback gain is given as 200. So we'll use this formula. This also we had found out, this also we had derived. So D is given to me, DF is given to me. So beta is the only unknown over here because A is also given to me. Okay, so I'll get beta from this, rearrange the terms, I'll get beta. Okay, soon after getting the beta, I'll use AF formula because I need AF. Calculate the gain with feedback. So I need gain. So AF is equal to A upon 1 plus beta A. Substitute, see if you get 20. The last thing now is to find out the output voltage. Now AF is what? AF is given as output upon input voltage. So output voltage I'll consider to be V out, and input voltage to AF will be not V in but Vs, correct? So from that V out will be AF into Vs. Okay, so Vs is given to me in the problem, okay, some 10 millivolts, and AF we have just found out. Substitute and get the answer. I hope this is clear to you all. These are some problems for practice. Again, you all need to send it to me by making a PDF. Please see to it that you all name your PDF with your roll number and name. These are some references. Thank you.